All right, let's dive in. Today, we're talking about a pretty revolutionary idea in artificial intelligence. It's a whole new way of building AI that doesn't just see a bunch of pixels, but actually tries to understand the world a bit more like we do. And it's an idea inspired directly by the wiring of the human brain. It all starts by figuring out what current AI gets wrong.
So, first off, just take a look at this. You can tell instantly this face is, well, it's a mess. The mouth's in the wrong place, the eye is all weird. It's completely obvious to you, but a really powerful, state-of-the-art AI might look at this and confidently say, yep, I see a face. So the big question is, why does a super smart AI get this so wrong when even a little kid wouldn't?
Well, this is what researchers have started calling the Picasso Problem. And it's a huge weakness in how a lot of AI systems see the world. See, they can be expertly trained to identify all the correct features. They know what an eye looks like, what a nose looks like, what a mouth looks like. But they have zero understanding of the spatial relationships between them. They see all the parts, but they completely miss the big picture.
So, what's causing this weird blindness to context? Well, the culprit is right at the heart of the most dominant type of AI vision today, the convolutional neural network, or CNN. For years, CNNs have been the absolute champions of image recognition, but it turns out their design has a fundamental, built-in flaw.
Okay, so let's really break down what these incredibly powerful networks are missing. It all comes down to a trade-off, a shortcut they make to be faster and more efficient. But what's the hidden price of taking that shortcut?
So, inside a CNN, there's this critical step called pooling. You can think of it like making a quick summary. The network looks at a little patch of an image and basically just says, okay, a nose is in here somewhere. And then it just passes that simple fact up the chain. It keeps the what, the nose, but to be efficient, it throws away the where, the precise location, the orientation, all of it. And that's exactly how you end up with the Picasso problem.
This slide just lays out the core difference perfectly. On one hand, you have what CNNs do, which is called invariance. They learn that a face is a face no matter if it's shifted a little. But they do this by just tossing out all that positional data. The new idea, equivariance, is a game changer. It means the AI knows a mouth is present, and it keeps track of its properties, its exact location, its angle, its size. It doesn't throw that crucial data away.
So how do we build an AI that actually understands these relationships? This brings us to the big idea from AI pioneer Geoffrey Hinton and his team, Capsule Networks. And this isn't just some small tweak. We're talking about a complete, fundamental rethink of the most basic building block of a neural network. So instead of individual neurons that just fire on or off, a capsule network uses these things called capsules. A capsule is basically a little team of neurons that work together. Their job isn't just to detect a feature, but to output a whole bundle of information about it, a vector that describes its properties in really rich detail. And this right here shows the difference brilliantly. A traditional neuron, it gives you a single number. A simple, yes, I see a nose. That's it. A capsule, on the other hand, gives you a whole list of numbers. A vector. It says, yes, I see a nose, it's tilted about 15 degrees, it's this large, and it's right here. It's the difference between a simple yes and a detailed description. Okay, so we have these capsules that are outputting all this rich information, but how do they work together to form a whole, coherent picture, like a face? Well, the answer is this really clever process called routing by agreement, which is basically how these capsules learn to cooperate and build a consensus.
You know, the easiest way to think about it is like a committee vote. First, you've got these low-level capsules that spot simple things like an eye or the curve of a mouth. Then, each one of these capsules makes a prediction. The eye capsule might say, okay, based on my position, I'm predicting there's a face centered right here. The network then just looks for a cluster of these predictions. And if the eye, the nose, and the mouth capsules all predict a face in roughly the same location and orientation, well, that's a really strong agreement. And that agreement is what activates the higher-level face capsule.
And here's the crucial part. This agreement system is incredibly robust. As the source material points out, the odds of multiple capsules agreeing on the properties of a complex object just by random chance are astronomically low. We're talking once in a million trials. This is what makes the network so confident and so accurate.
So, after all that complexity, what's the big payoff? What do we actually get from building an AI this way? Well, it turns out the advantages are pretty significant.
For starters, it just works better on certain tough problems. On the famous MNST dataset of handwritten numbers, Capsule Networks actually cut the error rates way down compared to a standard CNN. They were especially good at identifying digits that were highly overlapped,
which is a classic case where understanding the parts and their relationships is absolutely key.
And that's just the beginning. The source lists 4 major advantages. First, because CapsNets explicitly handle pose and orientation, they're naturally better at recognizing objects from different angles. Second, they can be more efficient, needing fewer parameters to get the job done. Third, they generalize better to new viewpoints they've never even seen in training. And finally, and this is really fascinating, they're much more robust against those sneaky adversarial attacks that are designed to fool AI.
This idea of viewpoint invariance is a huge deal. A traditional CNN has to be shown an object from tons of different angles to learn them all, but a CapsNet learns the underlying part-to-whole relationship. So by using these pose matrices, it can understand how those relationships transform from a new perspective. This allows it to generalize in a much more powerful and, frankly, a much more human-like way.
And maybe the most mind-bending part of all of this is where the inspiration might have come from in the first place. It seems this radical new idea for artificial intelligence might have a direct parallel right inside our own brains.
The source material points to this structure in the brain called the cortical mini-column. It's this tiny vertical column of about 80 to 120 neurons that are all densely interconnected and seem to act as a single unit. So, a group of neurons working together on a specific subtask. Does that sound familiar? It's a pretty striking parallel that suggests we might finally be on the right track to mimicking real biological intelligence.
All of this really leaves us with a profound question for the future of AI. That Picasso problem shows us the limits of just matching patterns in pixels. Capsule networks, on the other hand, offer a path towards something much deeper. An AI that doesn't just recognize but actually understands the structure of our world. So the real question is, are we just building a machine that processes data? Or are we on the verge of creating one that can truly see,